In this video, we're going to be talking about properties of trapezoids and how we can use those properties to solve for some unknown measures. So the first thing we need to do is state some properties and identify parts of a trapezoid. Trapezoids come in all kinds of different shapes and sizes, but specifically, they have to have one pair of parallel sides. So as long as they're a quadrilateral, four-sided shape with one pair of parallel sides, we can identify them as a trapezoid. Here are the specific pieces or parts of a trapezoid. The parallel sides are called bases. So those one pair of parallel sides are called the bases. So if you can look in the symbols, you'll see an arrow symbolizing parallel sides. So top and bottom here are the bases, but be careful. Just because they're called bases does not necessarily mean they're on top and bottom. We can look at a different type of trapezoid, specifically a right trapezoid because it has right angles. And if we rotate it so that it's facing this direction, the parallel sides are on the left and right side. So it just depends on the rotation of the trapezoid. You're always looking for the parallel sides. Those are the bases. The non-parallel sides are called legs. Trapezoids are really triangles with the tops cut off. So they would inherit those types of triangle properties. And we know that sides of triangles are called legs. So the bases, if you can identify them as the parallel sides, we can name using segment notation. So segment AB and segment DC are examples of the bases in this diagram. We could also flip those endpoint letters. As long as we're using capital letters and segment symbols, then we'll be okay. The non-parallel sides are called the legs. So these left and right sides are the legs. Segment AD or segment DA and segment BC or segment CB are the legs. The angles that are attached to the bases, and there are 4 of them in a generic trapezoid, are called the base angles. So angle A, B, C, and D are all base angles. We'll get a little bit more specific with those in an isosceles trapezoid. Let's talk about one more piece of a trapezoid. It's called the median. Just like medians of a triangle connect the midpoints of the legs, well, the median of a trapezoid is going to do the exact same thing. So the median is always parallel to the bases, and it's always going to connect the 2 midpoints of the legs. So point E is in the middle of segment AD. If it's in the middle, that means it just broke up this side into 2 equal halves. So segment DE is congruent to segment AE. And likewise on this side, point F is in the middle of segment BC, so it's splitting up that segment into 2 equal halves. So segment BF is congruent to segment CF. And we can identify the median as segment EF or segment FE. There is a way to figure out the median length. It's just an average of your base lengths. And hopefully this formula looks really familiar. Way back when we talked about midpoints, we used a very similar formula where it was the sum of the endpoints divided by 2. The median length is the exact same formula, just in terms of bases. So sum of the bases divided by 2, or the average of the base lengths, is your median length. We'll use that to solve for some unknown measures. All right, let's practice those properties. Here we're given trapezoid ABCD, and segment EF is the median. So we can mark up our diagram. We know that the parallel sides are the bases, including the median, that's parallel to the bases. So point E is a midpoint, making segment DE and segment AE congruent. And on the other side, F is a midpoint, making segment CF congruent to segment BF. So let's see how much of that helps us solve some of these questions. The first question, we're given values for AB and DC. AB and DC are bases, and knowing those base lengths will help us solve for the median length. So we can use our median formula. Average of the base lengths divided by 2 is the median length. And we're given those values. So 25 plus 13 is 38, and 38 divided by 2 is 19. So there's our median length if those were the base lengths. In number 2, we're given lengths for A, B, and EF. So similar problem, but slightly different in that we know one of the base lengths and we know the median length, and we're trying to solve for the other base length. So let's start off with the same formula, the same median formula, and let's substitute what we know. We know AB and we know EF. So we're going to solve for DC. To do that algebraically, let's get rid of that division by 2 by multiplying both sides by 2. And now we're left with 29 plus DC equals 48. And we can solve for DC by subtracting 29. And we find that DC is 19. So we can use that median formula to either solve for the median length, or if we know the median length, we can use it to solve for an unknown base length. But we have to know 2 out of 3 of those measurements. All right, in number 3, we're given AE's length, and we're asked to solve for AD. Let's see how AE and AD relate. AE is half of AD, or if I double AE, I can get AD. So let's do 2 times AE equals AD, or we could take AD divided by 2, and that would equal AE. So 2 times 11, 2 times AE gives us AD, which is 22. We're also given BC is 8, and we want to solve for FB. So let's see how BC and FB relate. FB is half of BC. So since we're given BC, let's take half of that, and we get FB. So 8 divided by 2 is 4. All right, one more example. Just a bit more algebraic expressions involved here. We're dealing with parts AB, EF, and DC. So again, bases and medians. Let's use our median formula and substitute the values that we're given, which allows us to solve for y. So the first thing we can do is get rid of that division by 2 by multiplying both sides by 2. Or we can combine our like terms up here in the numerator first and then multiply both sides by 2. Either way. We end up with 8y plus 1 equals 10y minus 6. Make sure you distribute that 2 to both of these terms here. Let's get our y's on the same side, hopefully get a positive y. So let's subtract 8y from both sides, which means that we're going to have to add 6 to both sides. So we get 2y equals 7, and we can solve for y by dividing by 2 and get 7 halves, or 3.5. So use your properties. The median property, which says that it connects your midpoints, or the median length equation to help you solve for base lengths or median lengths. Let's talk about one specific type of trapezoid called an isosceles trapezoid. And again, that's just an isosceles triangle with the top cut off. So it could be facing this way, it could be rotated and facing this way. Either way, the bases are still the parallel sides, the legs are still the non-parallel sides. But this time, because we had an isosceles triangle, we're going to have base angles that are congruent. And we're going to have legs that are congruent. There's also a third property of an isosceles trapezoid, and that is that the diagonals are in fact congruent, just like in rectangles. So if we use those properties, we can describe their parts based on this diagram. The legs are the non-parallel sides, and they're congruent. So segment AD is congruent to segment BC. The base angles are congruent, but we have to make sure that the base angles on each base are congruent, not all of them. So the base angles on this base are congruent. Angle D is congruent to angle C. And the base angles on this base are congruent. Angle B is congruent to angle A. And if we imagine the diagonals here, they would be congruent. So segment AC is congruent to segment BD. Running out of time, so I'm just going to show you these last examples and you can solve them on your own.